Hello, everyone. Welcome to a brief walkthrough of the Week 10 lecture notes. And this one, we're going to be taking a look at sorting, selection sort, and this concept of stable sorting algorithms and stable versus non-stable. So to go and get started with sorting, sorting is a very basic algorithmic procedure that we use in all of computer science. For instance, you might sort a deck of cards a certain way. You might sort numbers in ascending or descending orders, and you might want to organize how numbers are laid out. You have access to this sorts.py file that contains a ton of information about how to sort properly and very useful as well, like with the algorithms that are there. And in this video, we're going to take a look at the selection sorting algorithm. Now, before we delve into the selection sort, I want to talk a bit about what the difference between stable and unstable sorting is. And essentially here, let's just say that we went ahead and we had a list of items. Let's try to make it a bit unsorted, like so. Sorry. Let's say that we have like 4, 3, and then a 1, and then a 2, and then a 1 as well. So if we organize here, it's pretty straightforward that we'll say, okay, 1, 1, 2, 3, and then 4. Now, an issue is, though, which one is which? Is it this one this way, or is it that one? Or is this one here? Or is it this one over here? And essentially, you'll notice that there's actually no way for us to tell in this example which one is the one that is the one at the front. Now, that's fine for numbers, but let's just say that you're in a queue, and let's just say that not only do we have numbers, such as 1, but they have an identifier, like a badge or an X. So this one has an X, and then the queue is going from left to right. So, like, here's the end, and start is over here. And we'll say here, let's make this guy a 2 with a check mark, and then let's put this 1 over here with a check mark as well. And let's just say, okay, I'm going to sort these. Now I'm going to shift over the line and it's going to be numerical ordered. All right, so one goes first. And then the other one goes first, like so. And then my 2, which is straightforward enough, to hit the back because he has the higher number with his check mark. Which one in this scenario is the X? Which one is the check mark? Well, you would hope that if we're going from the start over here to the end over here, that the guy at the start over here is in this position, but it might happen that your algorithm actually sorts them like this. And this actually is not correct sorting. Even though the 1 is correct, this X should be behind the check mark that's here. Now, this is a very abstracted example, but essentially selection sort, which is the algorithm we'll code together shortly, is not stable. And of course, this will happen with it, with how we're going to implement it. These other selection sorting algorithms such as insertion and merge don't have this problem, and that's why we call them stable sorting. So that's the main difference. And again, you can look at the benefit here. Selection sort can be made stable, but it comes with quite a bit of storage price, and you can look that up as well. But essentially, that's the scenario where unstable sorting algorithms aren't the best. Now, to go ahead and get started here, the way that we're actually going to use selection sort is let's just take a list that's composed of elements like 4, 3, 6, 1, and then 2. Essentially, what selection sort will do is it will say, okay, take list of 0, and then go ahead and compare it to the remainder of the list. And then if any of these guys are smaller, then swap them. So essentially, you're going to keep doing that for each of these elements, and it's going to go through this. And the way that we're actually going to do that is by using a nested loop. So we're going to say, okay, press this guy, then go through all these ones. All right, he's good to press this guy, then go through all these ones. And we'll keep going down using this nested loop concept. And what we could say here now is let's go ahead and try to code this up with the sorting. So this algorithm is actually already coded for you, but I want to showcase how we can actually manipulate it a bit more. And one more thing about swapping is if I have a list of 0, and then I have a list of 1, what we're going to want to do here is not just go ahead and say list of 0 is equal to list of 1. Because if I type my list now, what happens? I actually get my item replaced here. So what we're going to want to do is let me reset this guy back to 4. What we're going to want to do is do a bit of syntax that looks like this. I'm going to say, you know what? Take list of 0 and take list of 1 and set them equal to the opposites of each other. So go ahead and say, you know what? Take the 4 to 3 and then put it to 3 and 4. Now, if I run this code now, we'll see that I've effectively swapped these items in place. So what we want to do is take this piece of code and sort them numerically or in ascending order. So it'll be 1, 2, 3, 4, 5, 4, 6. and I'm going to pass this method to them. So this method's not going to run right away. And what we need to do is make a nested list here. So what I'm going to go ahead and do is I'm going to make the size a variable called length of list. And because I'm going to be looking at a bunch of different values, such as in place or plusing 1, I might have an index out of bounds errors. So what I want to do here is I'm going to go up to the range of size -1, so I don't get out of bounds. And now to keep track of this number here, so we're going to need to keep track of the 0 and the 1 in our example here. But because we're looking through a list of any size, we're going to need to keep track of 2 types of elements here. So the first item that we're going to keep track of, I'm going to say tracked val. I'm going to set that equal to the current bottom that's a part of our code. So if we have this bottom level, and bottom could be, instead of saying bottom, I'm just going to say outer. It's going to be the outer item that's there. It's going to be set equal to outer. And then I'm going to go ahead and say go true +1 past the outer. And the reason that we do +1 is so that we don't look at the same item twice. If we didn't have the +1 here, tree would look at tree, 4 would look at 4, and then so forth. It would look at itself. So this makes it so that this outer loop doesn't look at itself. And then I'm also going to go through the size of my array here. And now I'm going to go ahead and do a simple check. So what I'm going to say here is, I'm going to say inner for this one. What I'm going to say is, okay, if the list at the inner index is less than the list at this tracked val that's given to me previously, what I'm going to say is go ahead and make tracked val equal to this inner. Now, after I go ahead and do that, what I'll say here, let's go ahead and try to print it out here. We'll see I tree a few times, but nothing really happens because I'm not swapping anything just yet. And we go ahead and try to return this list that I get from this code. And I'll go ahead and print the list that I get. We'll see that I'm getting, let me change this back to one tree. We'll see that because I'm not swapping anything, it's not working out too well. So I'm going to try to get the syntax here. So I'm going to copy and paste the syntax I made earlier. And I don't want to put it in this if statement. I actually want to go ahead and put it in my outer. So as soon as I figured out the position where my 4 should go and swap between one of these guys, what I'm going to say is, you know what? Take the outer one and not the inner one, but this tracked val, because inner is going to shift quite a bit throughout the code. We're going to want to just keep this tracked val there. And what I'm going to say is go ahead and swap them so that tracked val and outer are now swapped with each other, because outer is after the tracked val. I'll see here now that I actually go ahead and get 1 tree 4 tree 4, but my syntax is organized. So actually what happens here, and I'll actually print out the list so we can see in each iteration how it's looking. We'll see that I get a 1 in a tree. I go through each of these items that are swapped. Then I see the 4 and the 1 and 2 is swapped, and then so forth until I'm at the end of my list. And an issue is that even if it's already sorted, we'll see that I go through the end of it. So again, everyone, this is a brief introduction to a selection sort. Don't worry too much about the syntax behind it. It's more so the concepts that are going on here, where we look through each item and then make sure that it's sorted against it. There's also an algorithm online that showcases how these run in real time, and that's very helpful to do as well. And another thing, though, you'll see about this more is that we have this inner doubly nested loop. What happens if I have a list of 1,000,000 elements? I'm going to have to go through each element n times. So that means that I have 1,000,000 by 1,000,000. So this is actually a quadratic sized loop, which is not good. In the real world, this would not work at all, especially dealing with millions of pieces of data. But again, this is a very brief introduction to selection sorts, and should prep the way for our stable sorts later.